Hello and welcome. My name is Laura Waters. I work for Engineering and Scientific Innovations, Inc. Thank you for joining me today while I go over our tech talk on our shear stress measurement system for high-speed flow applications that we're currently developing under a contract with the Office of Naval Research. Engineering and Scientific Innovations, Inc., or ESI, is a woman-owned engineering R&D company located near Cincinnati, Ohio. Our company focuses in the technical areas of fluid dynamics and heat transfer, with an emphasis on experimental techniques and systems. Since 2013, ESI has been awarded 3 Phase 2 SBIR STTRs on experimental-based techniques. We own 3 patents related to acoustic noise reduction, lithium battery fire protection, and smart fire protection systems. Dr. Peter J. DeSimile of the University of Cincinnati is our principal expert. He has been working with shear stress-sensitive liquid crystals, the key component of our shear stress measurement system, for over 30 years. At ESI, we have a number of unique test facilities, including a Mach 4 wind tunnel, a nearly completed hypersonic wind tunnel, a deep water pool, and a large fluid acoustic test chamber. Over the years, we have had the privilege of collaborating with the Department of Defense, DoD, as well as many esteemed private companies on an extensive array of projects encompassing a diverse range of disciplines, from aerodynamics to aircraft survivability, resulting in the development of a unique fire protection system. ESI is currently working to bring the Smart Fire Protection System to market for aviation applications. The current challenge is to develop a high-speed, high-resolution shear stress measurement system that can be used to quantitatively measure the full field shear stress distribution on surfaces in hypersonic flows. Currently, only point measurements are able to be made. The capability to acquire stress levels over a large surface area will enhance both the Navy and the DoD's ability to design and test hypersonic vehicles. The expected requirements of this shear stress measurement system include a response time of 1 millisecond, as well as accurate full-field measurements over a large surface area in hypersonic flows with high spatial resolution. Our transition targets are air vehicle and weapon manufacturers, aerodynamic testing organizations, and CFD, computational fluid dynamics, code validation groups. The artistic rendering presented on this slide illustrates a fighter jet with a liquid crystal coating that is reacting to the hypothetical shear stresses that are on it. Understanding the shear stress distribution over a surface is a driving factor of all fluid dynamic analysis for aircraft design. Although CFD can be used to compute shear stress and provide insight over an entire vehicle surface, accurate experimental data must be available to first validate the necessary models employed within the CFD simulations, which to date is only limited to a few point measurement locations. While there are experimental visualization techniques that can be used to qualitatively infer the shear distribution over an entire vehicle surface, quantification of the acquired data has been unsuccessful to date. Shear stress-sensitive liquid crystal technology can accurately and quantitatively measure the instantaneous distribution over an entire aircraft or ballistic vehicle, significantly enhancing the design process. This versatile technology can be applied to flows with subsonic to hypersonic velocities. Shear stress-sensitive liquid crystals change color when subjected to a shear force. To date, this technology has been previously used to qualitatively visualize the shear distribution over various three-dimensional or non-flat surfaces. ESI has developed a method for calibrating liquid crystals so that the resulting color change experienced by a liquid crystal film when exposed to a shearing force can be quantitatively correlated. Using this technology, ESI is capable of quantitatively measuring the shear stress distribution over an entire surface for a wide range of flow regimes with a time response of less than 1 millisecond and a spatial resolution of less than 1 micron, or as accurate as the camera being used. ESI will soon demonstrate this capability at Mach 4 and Mach 5 during the Phase 2 option period. The image included on this slide shows the liquid crystal determination of shear stresses within and around the downstream end of a 120 by 10 millimeter yawed rectangular cavity in Mach 2 flow. While liquid crystals are incredibly unique and beautiful in their own right, they also provide us with a one-of-a-kind insight to an understanding that we've never had before. Non-encapsulated liquid crystals are shear stress sensitive and exhibit the ability to reflect light at wavelengths, color, dependent on the applied shear stress. It's incredibly advantageous that the shear stress-sensitive liquid crystals can non-intrusively be used to determine the full field surface shear stress distribution. ESI has developed an apparatus for calibrating the emitted color to a known shear force. Using high-speed digital imaging, ESI has successfully shown that the liquid crystals exhibit the temporal and spatial resolution for hypersonic applications. The use of such a technique will provide improved data relating to boundary layer transition on wings and surfaces of missile platforms, skin friction anomalies on high-speed platforms, rotary wing aircraft, highly maneuverable fixed-wing aircraft, as well as assessing vehicle-machine performance. There is no full-field shear stress instrumentation currently on the market, only costly single-point sensors and pressure-sensitive paints for determining surface pressures. It is known that liquid crystal technology has also been targeted by Russian and Chinese research communities, but no company has yet to emerge offering what ESI plans to offer: full-field shear stress measurements at low and high-speed capabilities on both static and dynamic surfaces, as well as low-cost data acquisition surfaces that can be performed at the customer's test site. Our schedule for the Phase 2 option starts with calibrating the shear stress-sensitive liquid crystal, the completion of the Mach 5 design, and then its fabrication. Once the tunnel is finished, we will then calibrate the shear stress-sensitive liquid crystal in the Mach 5 tunnel. With reporting throughout, we will finish with a laboratory demonstration of the Mach 5 wind tunnel and shear stress-sensitive liquid crystals. The current shear stress-sensitive liquid crystals are being provided by Hallcrest, a chemical company now owned by Spaatzy. Since Hallcrest Spaatzy does not have the aerodynamic expertise, the development of targeted shear stress-sensitive liquid crystal viscosity ranges was never a focus, but instead they covered a full spectrum of viscosities and therefore speed ranges. Optimizing shear stress-sensitive liquid crystal performance by adjusting their viscosity range would take place during the Phase 2 option. Discussions with Hallcrest Spaatzy indicate that either they would directly modify the liquid crystal formulation or provide ESI with raw shear stress-sensitive liquid crystal and thereby enable ESI to fine-tune the formulation. Formulations would be evaluated under different temperature and pressure conditions, those primarily associated with high-speed flight. ESI has already designed and fabricated a calibration rig for pressure and temperature correlation. Concurrently, Spaatzy Hallcrest has now made ESI a distributor and technical point of contact for research and development liquid crystal sales in the Western Hemisphere. Finally, demonstration of the resulting shear stress-sensitive liquid crystal formulation would be performed in the ESI Mach 5 facility, after which demonstration at both Navy and other high-speed DoD facilities would be pursued. At present, we do not have a primary transition advocate, but we are actively seeking one. As a high-tech RD, T&E company, we recognize that not all programs and organizations have the capital resources necessary to purchase the latest instrumentation or the manpower to operate and maintain the level of expertise needed to fully utilize any given technology. So ESI offers a two-prong approach with its customers. 1. A measurement system can be purchased outright, and ESI will provide the necessary training and technical support, or 2. ESI can come into a test environment and set up the necessary instrumentation, perform the test, acquire data, and analyze the data. Once the shear stress-sensitive liquid crystal system is finalized, this capability would be offered to the Navy and other DoD organizations, as well as commercial entities such as the Sikorsky Aircraft Company, Boeing, etc. You can always find us at www.esi-solutionsinc.com, but we'd love to discuss any potential needs you might have. Reach out today via email to our company president, Veronica DeSimile, or to our principal expert, Dr. Peter DeSimile, at the email addresses listed here. Thank you so much for your time. Take care.